variances. And variances and covariances basically are related to each other. And then expected returns for each of the assets. Now, if you think about the number of inputs that you have when you compute the covariances to get the portfolio risk, if you remember, if you have the number of variances and covariances was this. Actually, this is just the number of the covariances. So if you have 10 assets, how many covariances do you have to estimate? 10 times 9 divided by 2 is 45 covariances. So immediately, if you want to apply this to a relatively large data set to actually calculate what this ORP is, those are just the inputs. And if you have returns, how do you calculate covariances? If you remember, the way you did it in the project is by just clicking a button, but what is the logic behind the Excel? Well, each covariance is calculated like this. You have the returns of an asset, the returns of another, returns of X, returns of Y. The way you calculate the sample covariance, does anybody remember how to calculate that?
It's the two, or there's a few different methods. You mean like the variance one, or
Actually, to compute
it's the summation of the xi's, which is each individual x minus the mean of x,
right.
or return of x, yes.
So you look at the return of X, this observation, subtract the average of X, multiply that times each observation of Y that is aligned with the same observation of X. The average. And then, so this is equivalent of a variance, basically, is a square value. You repeat that for all these data set, and then you add them up, and then divide it by n minus 1. So this process is essentially this. The covariance between the returns of X and the returns of Y is estimated as the sum, the returns of X minus the average, the returns of Y minus the average of Y, divided by n minus 1. So just to calculate one of those 45 covariances, you would have to go through this very lengthy process. Yep. So computationally, this can be quite intensive, especially if you're doing like 20 assets, 30 assets. This is going to take forever. Questions? Now, just one thing to keep in mind: if you look at the correlation, the covariance between an asset and itself, how does this turn out to be? The covariance between the returns of X and the returns of X, using that, is the returns of Xi minus Rx bar, Rx I minus Rx bar, divided by n minus 1, which is the same as Rxi minus Rx bar squared divided by n minus 1. This is the formula for the variance. So the covariance between something and itself is the variance of that asset. So the algorithm that Excel is using basically is taking the returns that you select, the columns that you select, and then it calculates this product for the first against the second, the first and itself, the first and the third, the first and the fourth, and then it does the second and the first, and so forth. It does all the possible combinations. Questions? So the point I'm trying to make is that if you want to figure out what the ORP is, the calculations that need to be carried out, they're very complicated and they're very costly. So the question is, well, is there a way we can simplify this process? At least, maybe simplify this, because as the problem is described, we can easily end up estimating 100, 200 possible covariances. So let's see if we can come up with a process that instead of estimating these many covariances using this lengthy process, we can estimate them by using something that is much easier than this part right here. So that leads to something called the single index models. Single index models. The objective of the single index models is to provide an easier way to compute the covariances needed as inputs in finding the ORP. So there is some theory behind it, and we're going to start with an intuitive approach to it, and then eventually we get to the conclusion, and then we add details to it. So the general idea is this. Can I actually estimate the returns as my forecast plus an error term? So this is what I forecasted for today. This is what really happens. The difference between these two is how much I was off. Does it make sense? So this is a true statement every time, because the value that this takes is always going to be the discrepancy between reality and my forecast. Do you agree with that? Now let's make some statistical assumptions. So the error term is normally distributed. The error term is normally distributed. And what's special about the normal distribution?
It has a mean of 0.
It's no, the normal distribution is described entirely by two parameters. What are the two parameters? The mean and the standard deviation. So this is an important assumption that we're making. So in order to describe the distribution of this thing, if we pick the normal distribution, we only need to fully describe it by using those two values. So the first value is going to be the mean. This is the way you write normal distributions, and the second one is the standard deviation. Yep. So let's think about this. I'm trying to use this model to describe my ability to forecast. And let's suppose you're playing this game over and over again. So I make a forecast, then I figure some stuff out, then I make another forecast. I see how much I'm wrong, then I make another forecast for the next day. Eventually there is going to be some learning that goes on. So if your way of making forecasts is systematically biased, so you are systematically optimistic, So you're always wrong because you're always optimistic. The next time your goal is to make the correct forecast, what are you gonna do?
Gonna subtract away.
You're gonna subtract by normally what you're going to be off by, right? So you're going to, it's like when you're shooting, if you constantly miss your target and you keep shooting here, what are you gonna do next? The next time you're gonna aim a little bit lower. Maybe your sight is not adjusted right. So the only way this error term is consistent with the rational mind that is trying to make forecasts is if the average of your errors is 0. If the average is not 0, that means that your sight is adjusted improperly. You're aiming too high or systematically aiming too low. So you're failing to adjust for that. So in this model, an unbiased forecaster will have error terms with 0 average. Now, while you are sometimes you're forecasting too high, sometimes forecasting too low, reality is complicated, so chances are that you're almost never right. So your forecasts, your error terms, even though the average out to be 0, they will have some standard deviation called sigma e. Sigma e of I, sorry. So be careful with this, with the subscripts, because things are gonna get weird. Do you agree with that? So this means that on average my forecasts are not biased, but since there is some standard deviation on those forecasting errors, sometimes I'm forecasting it in excess, sometimes in defect, and I'm not accurate. Questions about this? No? All right, so can we make this model a bit more realistic? I mean, so far this is just concept. Well, if you look at reality, and you look at returns of assets, when you just did your project with ETFs, what are the correlations between assets? Are they 0 or are they some number?
Usually some.
They're usually some positive value. And so assets tend to have some degree of correlation. If they have some degree of correlation, that means that there must be something that is happening that simultaneously affect all assets. Do you agree with that? But those correlations they experience are not one. That means that some assets are affected differently by those common factors. So we can take this model and we can assume all assets are affected by a common shock. And we're gonna call this common shock M. So how would the model change? Well, the returns of an asset I at time t are equal to what is expected. But then, on this particular moment, there might be this shock that kicks in, and then there might be still this error term. Do you agree with that? So this term right here is the impact of the event that is affecting all the markets at the same time. Now, this common shock essentially is a surprise. Because if it was not a surprise, then it would have been included in the expected return in your forecast, right? So, what do we know about surprises? What should be the average value of M if it's a surprise? But the part that is meaningful here is the part that was totally unpredictable. Do you agree with that? Because if it were predictable, what would you do? it would just make a better forecast. So this M is such that but it's normally distributed. What should be its average? If it's a surprise, the average should be?
Not zero. No.
If it's, if on average there is a positive surprise, then you would expect that to happen and you would change that, right? So it's not a surprise, it's forecastable. So this M, in order for it to be a surprise, its average should be just like the error term, the average should be 0. And then there is some variability in its impact. So you have sigma M as a standard deviation. Yeah. So there are two sets of things that are going on here. There are things that you cannot forecast, we call them surprises. But then now we are allowing for two things to happen simultaneously. One is the part that you didn't forecast correctly, and then the one that just came out of the blue, that it was totally unforecastable. But this thing that happened, came out of the blue, is not you forecasting incorrectly the firm, but it's something that affects everybody equally. Now, conceptually, something that affects everybody and something that affects only your particular firm should be two things that are totally independent. So the other restriction when you make the model like this is that the covariance between the market-wide shocks and the forecasting errors must be 0. They're totally independent things. Okay, they're totally unrelated. So from this, we can say, well, what is the risk of I? Well, the variance of I, given those things and applying some statistical properties, is just going to be equal to the risk of M, the variance of M, plus the variance of the error terms. So just by making this simple assumption, we are decomposing the total risk of company I into two components. One that is market-wide, market risk, and another one that is specific to firm I. So we call it firm-specific risk. Okay. So just by allowing returns to be affected by a market-wide surprise and a firm-specific surprise, we are now decomposing the total risk of the stock into a component that is related to the market and a component that is unique of the firm. Questions? So, what do we know about reality? So this second version of the model is allowing for companies to have a common source of risk, right? We call it M. But are all firms equally sensitive to shocks in the market? No, so some companies are more sensitive to the same shock than others. So we can make this model even better. The model can be improved by allowing each firm, each asset to have its own sensitivity to market shocks. And maybe we can call this sensitivity beta. So beta subscript I is company size sensitivity to those market-wide shocks. So how does the model evolve at this point? Then the model becomes RIT is equal to what is expected of the company at that point in time, plus the firm's reaction, beta I, to market-wide shocks, plus the firm's crazy behavior at the moment in time. Do you agree with that? So how do things change? Well, it turns out that, again, if you look at the, suppose you want to calculate the covariance between, the variance of this asset using this thing. It turns out that the variance algebraically, the variance of I, can now be written as beta I sigma m whole thing squared plus sigma ei. So again, we decompose risk into two components. One that is proportional to market-wide risk, and the other one that is only dependent on the firm. We're gonna jump ahead a little bit, but how do we call these in the portion of risk that is linked to the market? Systematic risk. And how do we call this risk right here? The one that is not systematic is diversifiable or firm specific. So this is gonna be your firm specific risk. And this is systematic risk. Of company I, right? And what about the one before the equal sign? This is the total risk. Yeah, so it's the standard deviation or the variance of the returns of that asset. So we are looking at the returns of that asset and decomposing them into two sources of variability. One market-wide and the other one that is unique. Questions? So far, what do you need to know? You need to have a general idea where this thing is coming from, and how do we arrive to this? In general, we arrive to that by looking at a relatively simple scenario, and then we're adding more complications to it to make it more in line with reality. So you need to know this one, and definitely you need to know this one because you're going to have to do a lot of calculations using this. This is the final formula. Now let's suppose, what was our goal here? We wanted to find what the covariance is, right? We haven't done it yet. So let's suppose I want to calculate the covariance between the returns of X and the returns of Y. It turns out that the covariance between the returns of X and the returns of Y is equal to the beta of X times the beta of Y sigma m squared. That's it. So this is much easier than doing all of that stuff. The reason why this works out this way is because I didn't tell you there, but it's kind of, it should be intuitive to figure it out. if you're doing forecasts about two different companies, two different firms, what should the error terms be? How should they relate to each other? The error terms of company X and the error terms of company Y.
Be unrelated.
They should be unrelated, those are firm specific, right? So that's an important thing to keep in mind. The correlation or the covariance between the error terms of X and the error terms of Y is 0. Again, those are what? Those are firm specific. So with the firm specific, they should be unrelated one another. Questions? Let me make sure I didn't skip anything. That's it. I don't know how much this matters, but the derivation that we did is this part right here, all the way there, is actually called single factor model. The actual estimation of the betas using statistics requires you to use some index, like the S&P 500 or whatever it is, and so that, in that case, the empirical application of it is called single index model. So this is single factor. And the single index model is the empirical counterpart. Right, so how can we use this thing? Example. Before we get to the example, I guess let me add one more thing so you have all the notes together. What happens to betas? In a portfolio setting? So you can demonstrate mathematically that if you take those returns for one company, the same forecast for the returns of another company, and you combine them in a portfolio, so you do a weighted average of the returns, and you take averages. There are different steps you can take. Ultimately, what you end up getting is that the beta of that portfolio is just gonna be the weighted average of the betas. So they call that, in a portfolio setting, the return of a portfolio is the weighted average of the returns of the assets, where the sum of the weights is equal to 1, right, for the stuff that we've done. Can weights be negative?
Only if you allow for shorting.
If shorting is allowed, yes, weights will be negative, good. Then, applying these to the single factor model, yields the beta of a portfolio is the weighted average of the betas of the assets it contains. So it could be demonstrated, but I'm not doing it. Okay, so if you want. All right. let's start some applications of it. Example. An asset has total risk of 3%, a beta of 0.5, and the risk of the market is 8%. And the question is, what is A, systematic risk, and B, the firm specific risk of the asset. Okay. And then part C. What is the risk of a portfolio containing the asset and T-bills in equal amounts? Yep. Alright, so how do we find the systematic risk? The definition of systematic risk is beta I, sigma m. So, what do you get? Beta is 0.5, sigma m is 8, 4%. Yeah. What about firm specific risk?
The total risk.
Where you have sigma I squared is equal to beta I sigma m squared minus sigma, sorry, plus sigma I, sigma epsilon I squared. What are we looking for?
Looking for.
Sigma I, this guy. So just back substitute. You have 0.15 squared, subtract beta I sigma m, we already figured out is 4%. 0.04 squared is equal to sigma I squared. So what do you get? 115 squared minus 0.04 squared.
That number will come out to about 0.02.
0.02, do you agree with that?
Then you have to square root it to get.
0.15 squared minus 0.04 squared. Come on, quick, quick.
I got 0.0209.
Okay, so 0.0209. So this gives you what? This is the variance.
Yes.
So if the problem asks you for the standard deviation, what would you get?
0.144.
14.5%.
14.5%. 17.5%.
You still have the square.
I'm sorry, there is no square root. Do you agree with that? Questions? What about part C? You know, part C, we can't answer it, I haven't covered one thing. Yeah, I haven't covered that, so we cannot answer part C, just delete part C. Sorry. Make this disappear. Alright, so consider the following two assets. This is X and Y. Sigma. Between frame. And it's got the market is 8%. And the question is, A, what is the covariance between the returns of X and the returns of Y? B, what is the correlation between X and Y? So, covariance between X and Y, let's see. How do we find covariances in this setting? The covariance between X and Y is equal to beta of X, beta of Y, sigma m squared. Yep. So, is 0.9 times 1.1 times 0.08 squared. What do you get?
Zero point zero zero six three.
0.0063.
Yes.
Do you agree with that? Yep. So what about part B, the correlation? If you remember the correlation between X and Y is equal to the covariance between X and Y divided by the standard deviation of X times the standard deviation of Y. So we have the covariance 0.0063 divided by the risk of X is 0.18 times 0.2. What do you get?
0.176.
0.176.
176.
Yeah. So notice that we can compute those covariances very easily and compare that with these. But what is that we are assuming? That there is only one source of common risk, and this source of common risk might affect companies in slightly different ways. Each of them has its own sensitivity, and then the other part of risk is unique of the firms and is totally unrelated across companies. Okay, we calculated that. So I'm just making sure that we do all the problems that you have in the on the questions. So there is one problem that is more difficult than the others, and for this we kind of need to think about something. Consider two stocks or two assets. X and Y, okay? Let's suppose we want to combine those two assets in a portfolio. So let's go to portfolio P. Okay? And according to this model, the risk of P, just like the risk of everything else, should be modeled as being affected by two sources. One is the systematic component, and then there is the part that is unique of that portfolio. Okay, so this is the risk, the total risk of the portfolio is due to systematic factors. And then one part that is diversifiable or non-systematic. Do you agree with that? Now, based on what you already know from previous classes, if this portfolio is very, very large, what tends to happen to this part right here? What happens to
It goes down to zero.
the risk that we call diversifiable? It gets eliminated, right? But we don't know that yet. We're just saying, well, this is the way we are decomposing risk. So let's apply that to a portfolio, just like we did for individual assets. But also, there is another way to calculate portfolio risk. What is the formula for risk of a portfolio that you learned before? Is the weight of X, risk of X, square plus
Bit of Y.
weight of Y, risk of Y, square plus
2 times.
weight of X, weight of Y,
Covariance.
covariance, XY. Do you agree with that? Notice that this representation and this representation should yield what? The exact same amount of total risk, right? So those two should be the exact same. Do you agree with that? We're trying to calculate this total risk in two different ways. So we can use these and actually figure out what is the firm-specific risk of a portfolio. How can we do it? Well, if you can calculate the total risk this way, you know the beta of the portfolio, then all you need to do is set those two things equal to each other, and then take this away from that. That gives you this guy. So let me just write here. It could be useful in some instances. To set, to write the two equations together. So you have this first one, beta b, sigma m squared equals, oh sorry, I forgot the other part, plus sigma ep squared equals weight of x, sigma x, weight of y, sigma y plus twice. Okay. So let's see if now we can answer the question that I asked you in here, the part C, where we are creating a portfolio composed of those two things, and let's try to figure out a firm-specific risk of that portfolio. So the first problem, and compute firm-specific risk of a portfolio equally invested in the asset and the risk-free asset. Okay, so we are dealing with this scenario, and we want to figure out the risk of a portfolio that is equally invested in those two things. So for convenience, let's write what we have. This is the asset. This is the risk-free. What is the beta of the, but before we get there, what is the total risk of the asset?
15.
Total risk is 15, right? Okay, what is the total risk of the risk-free asset? Zero by definition, right? So this follows by definition. And what is the beta of the asset? Oh, so the beta of that asset is 0.5. What is the sensitivity? Let's go back here. We know that this number is not zero in this case because it's given. And the only way for you to get zero here is if this is zero, and by definition we know that the firm-specific risk of the risk-free asset is zero. Or this quantity right here is zero. We know that this guy is not zero, so the only way for that to happen is if beta is zero. So beta for the risk-free asset must be zero. Yep. And what about the weights? We are creating this portfolio equally weighted, so the weights are half and half. Yep. All right. So what about with this information, what is the beta, what is the covariance between the asset and the risk-free? Well, how do we compute covariances? Is the beta of the asset times the beta of the other times sigma m squared The value of the asset is 0.5. The value of the risk-free is 0. Sigma M is, I forgot, 8%. So anything times 0 gives you 0. So the covariance between those two guys is 0. So with all this stuff, we have enough information to write risk this way. You agree with that? So you have that WX, sigma X, this times that, and so forth. We have the weights, we have everything. So compute sigma P as variance with the traditional formula that we have developed earlier. So in this case, you have risk-free, and covariance, right? Do you agree with that? So what do we get? This is the risk of the risk-free is 0, so this guy goes away. This guy, covariance, we know is 0, so this goes away. So you're left with the weight of X, which is the weight away, 0.5, times the risk of X is 15%.